Welcome to the second part of the problem-solving session for Chapter 3. Here we have a problem that has a diagram showing a stubborn mule. Two students have each ropes that are trying to pull the stubborn mule. One student exerts a force F1 of 120 newtons. The other student exerts a force F2, which is 80 newtons. In the first part of the question, we're asked to draw a graphical sum of the vectors F1 and F2 and to show the resultant of that sum. So let's begin by drawing an XY coordinate system. X, Y. The first vector F1 makes an angle of 60 degrees with the horizontal, and we are going to add this vector to vector 2, which is F2, and there's no particular order here. We've just chosen to take F1 and add F2 to it simply because of the chronological sequence. But to draw the vector F2, we have to have the tail of vector F2 at the head of vector F1, and we draw a little makeshift XY coordinate system so that we can properly align the vector, orient the angle to match that which has been given to us, 75 degrees, with the horizontal, in this case, negative x-axis. Here again is vector F2. Now we have to draw the resultant. The resultant always starts at the tail of the first vector and ends at the head of the last vector. And so there is the graphical representation of the sum of the vectors F1 and F2. In the next part of the problem, we're asked to add the vectors F1 and F2 using the component method and to express the value of the resultant in unit vector notation. Now, to be able to do this, we have to obtain individually the x and y components of each of the vectors. So, to facilitate the process, let's go ahead and just draw the vector F1 on its own. Here we go. This is the magnitude of F1, being the length of the vector F1. And the components, we start with the x component, F1x, and F1y. We see that we have a right triangle, and the angle that is marked with the positive x-axis is 60 degrees. Now, trigonometrically, we calculate F1x as being the magnitude of F1, vector F1, which I'll just leave the absolute value signs off for now, cosine of theta, and we know it's positive because the component arrow points in the positive x-axis. Here we see that using the magnitude of 120 newtons, which by the way is the unit of force in the SI system, we obtain the component which is 60 newtons. F1y is given by the magnitude of F1 times the sine of the angle theta, which F1 y is also positive since it points along the positive y-axis, and we get a value of 104 newtons. Okay, now let's do the same for F2. Now we know that F2 lies on the second quadrant, making an angle of 75 degrees with the horizontal, and we proceed to obtain its components, F2x, F2y, And trigonometrically, f2x, note that it's negative since the angle truly from the x-axis would be 180 minus 75, in other words 105 degrees, and that would give us a cosine which is negative. Likewise, or otherwise, we might note that because the component points along the negative x-axis, we're going to have a negative component. Here, putting the values, 80 newtons times the cosine of 75 gives us minus 20.7 newtons, and F2y in this case is positive, gives us a value of 77.3 newtons. Okay, now that we have the components, we're ready to add all the x components and all the y components, and in this case, obtain, let's do this symbolically first so that you can see it, F1y plus F2y in the j hat. When we add the components, we get 39.3 I hat plus 181 j hat, and of course the unit will be the newton since we added two quantities each per unit newton. So this is the resultant of the pull of these two students on the mule. Well, the third part of the problem asks us to find the force that essentially the mule has to exert in order to resist the motion that it would otherwise experience as a result of the pull. Now, what that means is that for this mule to remain stationary, the equivalent force has to have the same magnitude as the resultant, but the angle has to be 180 degrees from the resultant vector. And to do this quite simply, we note that the x component of the resultant is positive, and so the equilibrant will have a negative x component, and the same will be true for the y component, and so the equilibrant is minus 39.3 I hat minus 181 j hat. Next problem. Here we are given two vectors, vector A, vector B, and we're asked to determine the scalar product of these two vectors, the magnitude of each of these vectors, and the angle between the two vectors. So let's begin. The definition of scalar product, sometimes known as dot product, between two vectors is magnitude of the first vector times magnitude of the second vector times the cosine of the angle between the two vectors. Now, we can easily obtain the magnitude of vector A. Let's proceed, which is the square root of 3i hat squared, giving us 9, plus 2j hat squared, giving us 4, square root of 13. The square root of b is 4i hat squared, or 16, minus, or plus minus 4j hat squared, also giving us 16, for a total of 32, square root. However, the problem is that we do not know the angle between the two vectors. Now, we can plot the two vectors graphically and then resolve the angle, the smallest angle between them. But another way that we can do this is to multiply these two vectors using the FOIL method of multiplication. Let's proceed and see how we might do that. We take the vector A, 3i hat minus 2j hat, dot it with the vector B, 4i hat minus 4j hat. And if you recall in algebra class, the FOIL method takes the first, multiplies with the first, and so we get 12 I hat dot I hat is 1. Then the first with the second, minus 12, but I hat dot j hat is 0, so we get no term here, plus minus 2j hat dot I hat is minus 8, except j hat dot I hat is 0, so no term here, plus 8 j hat dot j hat, which is 1. So this is 0, this is 0. In other words, we can simply make use of the fact that I hat dot itself is 1, but I hat dotted j hat is 0. And so we didn't even have to bother to multiply these terms because we knew if we had an I hat component, we could not obtain a result by dotting it with a j hat component. Anyhow, we're not finished. We have 12 times 1 plus 8 times 1 gives us 20. And so the scalar product is always going to be a scalar quantity. That's a pitfall prevention because a lot of times people will do this and then they'll say, okay, well that's I hat. Or they'll say something like 12 I hat plus 8 j hat. No, this is incorrect because when we dot the I hats and the j hats with each other, the value is 1. So the result of this scalar product is just merely 20. In the next part of the problem, we are asked to determine the dot product of the vector with itself. Okay, so let's proceed. The magnitude of the vector A is the square root of the vector A dotted with itself. Okay, that gives us 3i hat minus 2j hat dotted with 3i hat minus 2j hat, which is, again, making use of the fact that I hat dot I hat is 1, j hat dot j hat is 1, 9 plus 4, the square root of 13. But wait a minute, we got this earlier, if you recall. So effectively, we don't have to perform, effectively by obtaining the magnitude of the vector, we are dotting the vector with itself. And if you recall, and this would also be true for the magnitude of B, which we obtained earlier, again, it's the same result as taking the vector B, dotting it with itself, and should yield the value of the square root of 32. Now, in the last part of the problem, we're asked to determine the angle theta between the vectors A and B. Here, we are going to make use of the definition of the scalar product. A dot B equals the magnitude of A times the magnitude of B times the cosine of the angle between A and B, and this is essentially what we're going to be solving for. Now, we took the scalar product earlier and we obtained 20. The magnitude of A was the square root of 13. The magnitude of B was the square root of 32. So, solving for theta between A and B, we get the inverse cosine of 20 divided by the square root of 13 times the square root of 32, and this gives us an angle of 11.3 degrees. Next problem. Here we are given two vectors A and B again, And vector A has the components minus 3i hat plus 4j hat. The vector B has the components of 2i hat plus 3j hat. Let's just add a little term to the vector B just so that we can work with at least one vector which is three-dimensional. Let's say we add 4k hat to the vector B. The first question is to determine the cross product of A and B. Here we can use a matrix form to solve for this. I hat, j hat, k hat, and we place minus 3 for the vector A, 4, and 0, and then 2, 3, and 4, and proceed to solve the matrix. Let me show you another way, however. If we want to get around using a matrix, we might be able to remind ourselves the cyclical permutation of the unit vectors and use the FOIL method, which we may be very comfortable with, using that cyclical permutation. Let's proceed. A cross B is equal to minus 3i hat plus 4j hat cross 2i hat plus 3j hat plus 4k hat. All right, so first with first, but we know that I hat cross I hat is 0, so we get no contribution from this term. The next term, 3i hat cross 3j hat, well, we get negative 3 times 3 is negative 9. And I hat cross j hat is k hat, according to our cyclical permutation. Next, we have minus 3i hat cross 4k hat. That gives us a minus 12. I hat cross k hat is minus j hat. Okay, second term. 4j hat cross 2i hat gives us 8 for the numbers. J hat cross I hat is minus k hat. Okay, that was the first term. Second, we get 0. Third, plus 16 times j hat cross k hat is I hat. Now, we put it all together and we end up with 16 I hat plus 12 j hat minus 17 k hat. To get the magnitude of this vector product, as we were asked in the next part, we merely take the square root and square each component. 16i hat squared plus 12j hat squared plus negative 17k hat squared. And remember, when we square I hat with itself, we get 1. And the same for j hat with itself and k hat with itself. Putting it all together, we get 26.2. Now, you may be tempted to have used this expression for the magnitude, and it would have been fine, which is the magnitude of the vector A times the magnitude of the vector B times the sine of the angle between them, except you don't know the angle between them. The last part of this problem asks us to solve the angle between them, so you might want to use this expression to do this. Word of caution, do not use definition of vector product or the magnitude of the vector product to determine angle. Why? Because if one of the vectors happens to lie in the second, third, or fourth quadrant, you will get the wrong angle. You will get the outer angle, the angle between the larger of the two angles as opposed to the smaller. And you would not know this unless you've plotted each, in which case, why even bother to do this? You can work it out. So the safest way to obtain the angle between the two vectors is none other than the dot product definition. Here, A dot B divided by the magnitude of the vector A times the magnitude of the vector B. So let's see if we can quickly obtain A dot B. Gives us minus 6 plus 12, which is 6. Magnitude of A gives us 9 plus 16, which is 5. Magnitude of B gives us 4 plus 9 plus 16, which gives us the square root of 29. Plug everything in, and we get an angle theta between the vectors A and B of 77.1 degrees. This concludes the part 2 of the solutions to the problems in the lecture notes of chapter 3. Until next time.